Welcome everyone, and my name is Dennis Helsel, and today we're going to be talking about the NADA2 package for R. We're really talking about all of the many things in statistics you can do right now with data that have non-detects. So let me go ahead and get us started. The NADA2 package is a new package that will be available soon. It's made up of routines that have been used in our online training course, Nondetects and Data Analysis. And if you're wondering how many kinds of statistical procedures you can do with Nondetects, the answer is just about everything you can do when there are no non-detects. When this is recorded and up on a recorded page, which will be on our online training page, the link to download the PDF will be just below where the video is. You may also submit questions during the webinar, and I would encourage you to do that during the webinar, and then afterwards. It's a lot easier to remember what your questions are if you do it during. I will answer those, not live today, but over the next 2 days, and then put the Q&A file along with this webinar recording at our online training site, practicalstats.teachable.com. All right, let's get started. I'm first going to start with an introduction, which is what's wrong with substituting things like 1/2 the detection limit. I'm going to make that really short. There's a webinar on that issue. There is a short video on our videos page at practicalstats.com, like a 15-minute video on the same topic. I'm just going to do a small piece just to remind you of that. And then for essentially the whole webinar, I'm going to be doing a survey of statistical methods for data with non-detects. What are the methods that are available right now without substitution? And then finally, I'll tell you about the NADA2 package for R, although it's going to be all these routines that I'm talking about prior to that. And then I will tell you that it's going to be available sometime in the first quarter of 2021 on the R CRAN site, where you download packages, you install them, and then you can load them and use them. And so the NADA2 package will be there. My intent is sometime in January, but I'll fudge a little bit and say it'll be within the first quarter. As I go through this, I know I'm going to be talking about censored data. So just to define that term for you, that's a statistical term. That means that the values that you have are known to be only below a threshold or above a threshold, like less than 1, where 1 is the detection limit, and you don't have a unique value for each observation. So they're just recorded as less than that threshold. There's a lot of information in those, and that's what using them is all about. You do not want to throw them away, and you do not want to substitute a number for them. Methods for censored data have been used in the medical statistics world since the 1950s, and so the NADA2 package just takes advantage of those procedures and makes them a little bit friendlier for data that are less thans. The packages that are written are often for data that are greater thans, above a threshold. But we deal with less thans. All right, so what's wrong with substituting a number like 1/2 the detection limit, or the detection limit, or 0, or anywhere in between 0 and 1 times the detection limit? What's wrong? It adds an unintentional, artificial pattern to the data. So here's a set of data that I generated. It's the only thing that I'm going to show you, I think, in this webinar that's been generated on a computer, just to make it a nice straight line with noise around it. Looks a lot like data that I've seen, except it probably has a bit better slope to it than some of the data out in the field. And if you compute Pearson's R correlation coefficient, it has a value of 0.81. That's a fairly strong correlation. And so this would be something that you might want to fit a regression line to, etc. Looks like concentrations is a function of distance, maybe downstream or down gradient. Now, if I set two detection limits, one up around 3, so fairly high, one at 1, and I'll have less than 3s and less than 1s in the data set. And so I might say, well, for those less than 3s, I'll just call them all 1.5. And for those less than 1s, just call them 0.5. It would look like this. The 3 detection limit was there most of the time. What are you doing? You're adding a pattern. So don't just think about substitution as something with one observation, and it's somewhere, you don't know where, between 0 and 3. So you say, well, halfway, that's good enough. I'll just do 1.5. The problem is you're doing that over and over and over again and putting in a pattern. And that does a couple of things. First, it primarily lowers the variation in the data because you've just put in a bunch of numbers that are all exactly the same. And so it generally lowers standard deviations. And what that does is it gives you confidence intervals that are too short, gives you p-values in tests that are not correct. It gives you incorrect decisions in regression as to which x variables ought to come into the model and which should stay out. It gives you some incorrect ways of computing a surface in Kriging because it messes up the variation, it messes up the variogram, and more. So I've repeated the figure here just to show you, as far as particularly for correlation and regression, what you have done is to put in a nice flat zero slope line with a little bit of another line down here which also has a zero slope. So what has happened, Pearson's R decreases to 0.55. So it's lowered the amount of correlation that's observed here. And the computer doesn't know that these flat line points are not real. You should know that they're not real, but it doesn't. So it waters down correlation. It waters down the slopes. The slope that would be computed from data looking like this will be lower than the slope in that original data. And so you're going to put a lot of artificial information there that was not there in the original data. You're putting in a very unrealistic model and blending it in with the data that you have, that you can see, the detected values. So it's a bit like having a really good cup of coffee, throwing away half of it, and then diluting it, putting water in for the rest of it. You've really just diluted down the signal, and it's not a good practice. So the rest of this webinar is about what else you can do. And I've just listed the things I'm going to talk about. I'm obviously not going to spend a lot of time on each one, but you can plot data and compare the shape of that data to standard distributions like a normal distribution, log normal, gamma. You can estimate means, confidence intervals, UCL 95s or other ends of confidence intervals. You can run hypothesis tests between groups. You can statistically run a test and compare the data that you have to standard values. You can compute correlation coefficients, build regression models, build good models because you evaluate whether the residuals from the regression model match the assumed distribution. Many regression procedures assume a normal distribution. Helps you decide if they're not that way, what you should do with the data, like transform the y variable, take logs of the y variable, etc. You can build fancy multiple regression models. You can compute non-parametric regression. What I mean by that is the Thiel-Sen line that you're familiar with, perhaps. It's used a lot in trend analysis. And you can do that for censored data. It's then called the Akritis-Thiel-Sen line. So you can go ahead and use that and perform trend analyses, parametric ones with regression, non-parametric ones with the ATS, the Akritis-Thiel-Sen line. You can do the seasonal Kendall test. You can draw multivariate plots, do cluster analysis, test hypotheses, whether groups are different when your y variable is actually 31 different variables or 103 different variables. So in a suite of variables, looking at them in multivariate space. And you can do Kriging, spatial statistics. All of this you can do without substituting numbers for non-detects. without throwing variables that have censoring away, which people sometimes do. If you'd like to know more information on this than what we have in the webinar today, our online course has been going for about 1.5 years. It's Nondetects and Data Analysis. It will have already right now in that course the NADA2 routines, and also will tell you a lot about the methods and how they work and why they work. So that's at practicalstats.teachable.com. That is a cost. It's not free. I'll tell you about some more free information at the end of the webinar. So let's go through that list of procedures. Here, you could compare data to a distribution shape. This is a NADA2 command called send compare QQ. So it's doing QQ or probability plots. It's plotting dark circles here for the detected values, but the positions of those on the plot are affected by the nondetects. So for example, if you had one detection limit, it was down at the low end, all the detected values were above that one limit. And let's say you had a half of your data, 50% were less than 1 or less than whatever the detection limit was. You'd have a plot like this normal QQ plot where it would be blank on the left side all the way up to 0, which is where the mean and the median are located for a normal distribution at 0. So the lower 50% are all going to be nondetects, and this will be blank. And then the points start above 0 at the 50th percentile and go on up. And so these kinds of plots take into account the nondetects when it's computing what quantile or percentile. This is just a linearized set of percentiles with the 50th percentile at 0 in the middle. It is just putting all of the detected values at their positions that they would have if there had been all of the data above the detection limit. You would have seen the left-hand side where those points were if there were no nondetects. Now you don't see them, but it preserves the position on the plot. So it's built for censored data. So you need to use routines in censored data procedures to get these. And so you can compare them to standard distributions like this. You can compute box plots and plot them. So here's the C box plot command. I'll show you several of these. All of these commands pretty much start with the column that has the numbers that are the detected values plus the detection limits, and then an indicator column that tells you which are which. Those indicator columns could be 1s and 0s. They could be text that say detect and non-detect, or it could be text that has a less than sign for the non-detects and it's just blank for the detected values. Things like that can go in here. I'll tell you more about that C box plot later. I wanted to get to computing means. This is actually a routine that is not in the NADA2 package, but is already in R right now in a package called ENV Stats, which has a number of good routines for censored data. And so it would compute here for this data set of pyrene concentrations. There's 1, 2, 3, 8 detection limits in the data set. And without substituting any numbers for those, it's computing the mean and the standard deviation for those, and a little bit further down the lower and upper confidence limit, 95% confidence limits on the mean. It's computing the statistic with the Kaplan-Meier procedure, but in ENV Stats is provided other methods as well for computing these. The Kaplan-Meier is a good one for multiple detection limits, and it's a non-parametric method. And then it's computing the confidence interval here because I've asked it to in the command with the bootstrap procedure. So none of what's here assumes a distribution, which is nice. I'm putting on each of these slides the code in R to run whatever it is that I'm showing you the results of, so that you can see how you might do it. Here's the box plot procedure again with a variable called thiomethoxam, which is a nicotinoid pesticide, I believe. So that's its concentrations and detection limits, and then the indicators, and then it's grouped into 4 groups by the variable sampling event. You can throw in additional labels and show the boxes, whatever they are, below the highest detection limit. Here, there was one whopping outlier in this data set, so I've just set the maximum to 20 so that you don't see that one outlier, which is going up here with this whisker. It's going to go way up, probably up to the ceiling. But that lets you zero in on the boxes and see them more clearly. So there's a lot of options in this command. And then after we've plotted the data, we could do a test. This is a non-parametric test. It's something like a censored version of the Kruskal-Wallis test. So it's a one-way or one-factor test. Do the concentrations for thiomethoxam differ by the sampling event categories, those 4 box plots that we saw earlier. So it does this test without substituting any numbers, and it can work fine. Everything I'm telling you today works fine with multiple detection limits. Gives you back a chi-squared statistic and a p-value if you're familiar with p-values. A high p-value says no signal, a low p-value, which this is, it's an extremely low p-value. It says there is a signal. The signal here is that the groups differ. It's testing whether their percentiles in each of the group are the same or not. Or another way of saying it is whether at least one group is different from the other. Is it sitting up higher or down lower than the rest? And this is about the smallest p-value I've ever seen coming out of a test statistic. After you've found a difference, you can do multiple comparisons. So you can compare pairs of the 4 groups. So we see that the pre and post group are not different. That's a number that's, quote, high. And then pre versus corn tassel and goldenrod are both low, very small numbers with a lot of zeros. 15 zeros before the 6 or something like that. The post data are very different than the tassel and goldenrod, and the corn tassel and goldenrod themselves, those are the 2 groups where there are not many values above the highest detection limit. I think that might be the only detection limit in this data set. There's not many of them there, just a few in the corn tassel group. So those are declared not significantly different, although it's very close to what the traditional limit of 0.05 is. I won't say much about it in this, but I'm not a strict 0.05 person. I would say that these are different, but that's another story for another lecture. You can also do things like put the Y variable on the log scale to see things better and color the boxes based on the results of your pairwise comparisons so that the boxes with the same colors are not significantly different and the boxes with different colors are. So there's a lot of ways that you can do things with the C boxplot command, the censored boxplot command. Okay, moving on to correlation. Without substituting anything, you can compute a correlation coefficient that's a lot like Pearson's R, called likelihood R, and its value, this is not the plot of the data, by the way, this value is 0.82, so it tells you that there's a fairly strong correlation between these 2 variables, which are the lead in blood and the lead in kidneys. This is in herons, I believe. There are other correlation coefficients as well. I'm just going to talk about this one for right now, just because it's the most similar to Pearson's R. It's not similar computationally, but it's similar in kind of the way the scale functions. And it gives you a p-value that says this is not 0. So we do have a significant correlation. Over here, I've just plotted the data, actually their residuals, which is what is concerned in regression, and showing that it's the logs of the Y variable, the logs of lead in blood that should be taken in order for this to look like a normal distribution. So it fits a log normal distribution better than a normal. And so I'll use that when I do plots. So here's a plot of the log of lead in blood versus kidneys. This looks like a straight line. It would not have looked like a straight line if I had not taken logs. So if we were going to do regression on this, or for this Pearson's R type of correlation coefficient, it is also, like Pearson's R, a linear correlation coefficient. It would be better and more accurate if you get the data to look like they're straight. So the logs of Y versus X look pretty straight. Notice here there are dashed lines coming up from the bottom. Those are the Nondetects. Those are used in this kind of procedure in this way, that you can look and see, well, how do these non-detects, which are all less than some small number, this is going from 0 up to that detection limit. So it looks like these all are at the same detection limit. How do they function as a function of the X variable? All of them are down here in the low values for the lead in kidneys. We don't see any to the right. So it's with the low lead in kidneys where you see low lead in blood. And that kind of information is used in these procedures. So non-detects do affect the results of these plotting procedures and the correlation procedures and what we're just about to look at, which are the regression procedures. So they should not be deleted. Here is sendCorreg, another command in NADA2, doing the Y variable and the X variable. The default is actually going to take the log of the blood lead data. You can change that with some options, but that's the default because it works most of the time with the type of data in environmental science. Gives you back these correlations again, and then down here you get something like a regression output. It is a regression output. You get a slope. Here's the slope of lead in kidneys, and the Y variable is the log of the lead in blood, and that slope is 0.24. Gives you a p-value for that, which is small, saying it's significant. You should keep kidney lead in as a predictor of lead in blood. You can use that, write out that equation, the intercept and the slope times kidney lead for the logs, and then you can exponentiate it, and then you have this equation, which will be back for lead in blood in the original units, and that will look like a curve. And so you can plot them in that way. So you can do simple regression with one X variable. You can do multiple regression too. Here, what you do in NADA2 is to set up different combinations of X variables. And so here I've put in 2 X variables, a different data set, which has population and depth for the 2 variable X variable model, then population density, depth, and land use as a 3 variable model, population density, depth, percent industrial land use, and then land use as a 4 variable model. And we want to know which is the best model. The procedure to do that is with something called AIC. It's used when there's no censoring. It also is a good one to use when there is censoring. It's a measure of error. So we'd like AIC to be low. And so if the model that has the lowest AIC is the best. AIC works far better than R squared with these kinds of things, even though you can get back R squareds for all of this stuff. I don't pay much attention to it. So with this is the 4 variable model. It's an AIC of 395.8. There's no good or bad AIC. It's actually a sum of a whole bunch of individual errors, one for each of the points in the data set. So there's no magic number, but you just want to get the lowest number you can with different models. So 395.8, essentially 396 for the 4 variable model. And it does give you slopes over here for the 4 variables and their p-values. It looks like with a 4 variable model, only population density is significant. The 3 variable model, I've tossed one of them out. Here are the slopes, here are the p-values. Again, only population density looks like it's significant, but the AIC has dropped from 396 down to just a little over 394. So this is a better model. The 3 variable model will give you better predictions. It's a better fit than the 4 variable model because that extra variable was just noise messing things up. How about a 2 variable model? We can drop one of these out. So I dropped the percent land use, I think, out. We've just got population density and depth, slopes for both of those, p-values for both of those. Notice now the p-value for depth is 0.06. That's down dangerously close to 0.05. So if you don't take 0.05 too literally, and you should not, I would say that's a variable that ought to be kept in the model. I generally, with AIC type fits, would pick anything that's less than 0.1. These things by simulations have been shown that they generally underfit. They generally don't bring in some variables that they should. So they're a bit too strict. And so if you get something pretty close like this, At 0.06, you ought to leave it in the model. And again, that's kind of in statistics these days. The 0.05 kind of approach is really grayed out quite a bit. So, and that's a good thing as far as the way that we know a lot more about the way these methods work now than we used to. So this would be a pretty good model, I think. Both of them seem to be significant, but let's just check. What if I did drop out depth? It's above 0.05. We have our AIC here that was all the way down to 393.5. And when I drop out depth, the AIC jumps back up to 395.5. So it jumps up quite a bit. So this is not anywhere near as good of a model. So AIC helps you decide which way to go on those close to 0.05 things. But in general, I think anything below about 0.1 would be something that would be a reasonable X variable to include in the model. And all of this I did without substituting any numbers for Nondetects. But the Nondetects effects are still in there in the positions, again, in the plot of X versus Y and the multiple Ys. Are there things that tell you that all of the Nondetects are at the low end for that X variable? Then that adds some significance to that X variable. Low goes with low and high goes with high for X and Y data. All right, non-parametric regression. You can do that. The accretus, the ascend line, it's the ATS command in NADA2. You can, with ATS, have censored values for both Y and X. That's not available yet in regression. Regression, the X variable is not to be censored. So I put this in, you get back another intercept and slope, familiar. I'm using the log of blood just because that's straight. It doesn't really matter in terms of normality because this is a non-parametric procedure, but you do want still the pattern of data to look linear because we're just building a linear model here. So I've kept the log of blood here. Gives you back another correlation coefficient, a non-parametric correlation coefficient, Kendall's tau, which is about 0.2 less than Pearson's R as far as its scale. So this is kind of like a strength of 0.6 on a Pearson's R scale. If you could translate from one language here, Kendall's tau language, to a Pearson's R language. At any rate, it's very significant. And so we do have a strong correlation between log of blood and kidney in terms of their lead. You can again plot that equation and note where the Nondetects are sitting. We could also take this back into original units and it looks like a curve. All right, so one of the uses for the ATS line is to do trend analysis with censored data. So here we could do something like multiple regression. What we're going to do is smooth censored Y values versus X's, where X is not a time variable. So it's the other variables that would be in the equation besides time. The smooth for censored data is something called a generalized additive model, or GAM, G-A-M. It could be multiple X's that are being used to create the smooth. I'm just showing you this with one X. And then you take the residuals from that smooth and run ATS on the residuals to get a Kendall's tau type change over time. So it's an ATS where the X variable for the ATS is time, and the Y are the residuals from that smooth. So what we're doing with the smooth is factoring out the effect of all of those other variables so that the only effect still in there is time, and then run the ATS trend test on time. Here's the smooth for a data set of chromium versus streamflow. And it's not a straight line. It actually bends up a bit right at the very end. I went up too far with the cursor, but it does bend. It's not a straight line. So this is a result of a smooth where you have input to the smooth. That's both the detected values that you see as points and the non-detects, which in this data set also are only present down at the low flow range. There is one all the way up here, which might be an interesting point to look at, why that is the case. So you can smooth the data, then you would take the residuals. So you take a value for the point, subtract off the value for the model here, the smooth, for the same x, and that's a residual. And do that for all of these points. You can also do it for the detection limit type residual here, and then submit that to the ATS procedure. Here's the ATS line on the residuals. And we have an equation for the residuals, which is a valid slope, the minus 0.0225 for deck time. It's a valid slope for the change over time once you adjust for those other variables. And the p-value is 0.03, so we have a significant, in this case, downtrend. You can also do the seasonal Kendall test. Here the data are broken up into groups called seasons, can be used for other things, but some groups. The trend analysis is run separately for each group, and then it's put all back together to give you an overall trend. Here's the overall trend line, I believe, for this chromium data versus time with the ATS line. The groups are seasons that are dry season and wet season. When trend test is run on just the dry season data, we get a downslope of minus 0.03, or basically 0.04, and a p-value of 0.009. So that is significant. Pretty small number. In the wet season, there is not a significant trend. So that can be important in your interpretation of this. And then it puts all these together into an overall test with a p-value of 0.014. So a significant trend overall, although that really is occurring in the dry season. You can get back plots of the individual trends for each season. You can see that for the wet season on the bottom, the slope is not much different than 0 given the noise in that plot. So it's not surprising it's not significant. All right, we're going to move on to multivariate methods. Multivariate methods provide a clue for how to deal with non-detects in a big data context. So often we have fairly large data sets, at least for us. We might have 120 different species of plants, and we're trying to say something about how that community structure changes. So that's the Y variable, if you want to think of it that way. The set of 120 species is the Y variable. How that changes with maybe time to do a trend analysis. Maybe in groups, one group looks like it's a pristine area and another group's been trashed by people in some way. So you'd like to test to see whether that community structure has changed in those two groups. You can do all of that, and you can do plots related to all of that. And you can do all of that without substituting numbers. In fact, it's much better if you don't. Not substituting numbers for non-detects. There's three approaches, kind of increase in precision. The first is binary. You could convert your data just to a detect and non-detect. So they're really just 0-1 variables. And you can do all of these various procedures, including cluster analysis and plots and trends and everything else. But a little bit more precision is to rank the data. So this is going to be a non-parametric procedure. We're going to rank the data. You could say that a less than 1 is less than a 3. And so you would rank the data and use those ranks. I'll show you how in a second. And then there are things called U-scores that are used in a variety of different statistical procedures. And those U-scores can handle multiple detection limits, at least to some extent. So the binary approach in multivariate procedures, what you're trying to do is look at pairs of points. It might be 2 different sites or 2 different times. And then take those 120 variables, boil them down into some statistic that measures the similarity or distance between those 2 sites. And then do that for every possible pair of sites. So this is the simple matching coefficient. The things we're matching are 1s and 0s, whether this is below the detection limit or above the detection limit. The ones in NADA2 by default, though you can change this, the ones are below the detection limit, so these are yes, censored, and the 0s are no, they're not censored, they're detected. So if you had two different sites, J and K, and they were both non-detects, or they were both detected values, that's a measure that they are similar. If they differ, below versus above, there's two ways to do that, then they are less similar. And so we're just going to look to see if this pattern of similarity, by looking at this, the similarity and differences differ, say, by time or across and between sites and locations. Here's the first 6 rows of a data set, an old data set with DDT and some metabolites. And there's ortho and para versions of them, if I remember my terminology right. Here are the numbers in the first column, which could be detected numbers, or it could be detection limits. The ones here look suspiciously like detection limits of less than 1. Over on this side are the indicators. That's the second variable that's put in. So 1 if they are non-detects. So that 1 there says that the value in this column was a less than 1. The 0 that's here says that this 14 was a detected 14, and so on. We see that row 1 has a similar pattern. In fact, it has the same pattern of 1s and 0s in row 1 as it does in row 5. And so row 1 and row 5 would end up looking fairly similar. So with this binary approach, you're really just looking at this set of columns, the indicators. And from those, you can come up with the distance measure, the simple matching distance measure between sites, and plot those distances on something called non-metric multidimensional scaling. And so the distances shown on the plot are in the same rank order as the distances in the data set. So these values for sites 25, and I believe underneath that overlaying it is a 1, and 5, and 24, and 26. These all look very close. 6 is probably not far away. Those are all young fish. There's a grouping variable here of fish that were aged somehow, and they were either young or mature. And then all the black dots are the mature fish. So this first x-axis direction here is really a scale that's going from young fish to older fish. And that's all based on the pattern, not of young and old. That's just used to color the dots, that variable. The pattern here of the positions of the points are from the, let's say it's 120. In this case, it's only 6 variables, but the 6 variables, or the 120 species counts of organisms and that sort of thing. So all of that can give you a picture of which sites look like other sites. And the second axis here tells you that site 30, even though they're both mature, is somehow pretty different than 23. You can do cluster analysis with the same data. So this is something where the grouping is not predetermined. The young versus old thing is not used at all in doing the clustering, just the numbers. And the young data are all stuck in the same cluster. So they were seen just by the pattern of DDT, DDE, and whatever the other one was, that they are all similar to each other in this young group, and these two other groups were all the mature fish. You can do something similar for ranked data, except it's a different metric. It's the Euclidean distance. So this is a distance, a straight line distance in multidimensional space. And you would do that on the ranks of the data. And so these routines that I'm just flashing up here, ordranks.r computes these ranked data within all of the different columns. You're doing ranking within a variable, not across variables. So each variable could have its own detection limit. This is a 1 detection limit or highest detection limit procedure. But each variable can have its own detection limit. And then the routine in NADA2 called meta-MDS does the non-metric multidimensional scaling for ranking procedures. And it puts the young fish again on this side and the mature fish over here. You can do tests. Are the young fish different than the older fish in terms of its pattern of the 6 metabolites or 6 variations of DDT? So this is a permutation test, and there's only about 1% of the data that are at the observed value of 0.29, which was the test statistic for our data. There's only about little over 1% at that value and higher here. That's what the p-value is, 0.013. So it's telling you it's a fairly unlikely result, and we would then reject the null hypothesis that these are the same. The blue bars here are really a picture of the null hypothesis and what it might be. This is a permutation test. And so we would find these groups to be different in terms of their pattern of DDT congeners, I suppose. And you can cluster those ranking groups as well. And again, the young fish all turn out to be in the same cluster. And the U-scores, I'm not going to go into them in any measure, except that it's a way to compute distances that can account for multiple starting points, multiple thresholds. So they're used in other disciplines. They're used in other procedures too, like in the Mann-Whitney test, in Kendall-Stau correlation, are using these things called U-scores. So you can do that to compute distances in multidimensional space, accounting for multiple detection limits. And what I did here was I actually made site 1 a different detection limit than the rest of the sites. I don't think they were originally. Just to show you what happens when that happens, the ones with all the same detection limit look similar here. It's telling you that the site 1 is different somehow. And you'd have to go back and see, oh, that was a higher detection limit, and so it's less precise in terms of its results. It doesn't know really whether to put it into that group or maybe to this group, because this detection limit might be higher than many of the concentrations measured in the other group with the mature fish. You can do the NMDS plots. Again, it puts site 1 away from the other young fish. This is still kind of a young, mature scale, but 1 is out here with some of the mature fish. You can do a trend test over time with these same kinds of statistics and get back a significance that it's 1 times 10 to the minus 4th. It's a very small number, so we do have a trend with the U-scores. And then finally, for our final type of procedure here, you can do spatial statistics without sticking in a half. And just to tell you a very brief description of these spatial statistics procedures, what they're doing is a fancy regression, except the regression is including the correlations between sites, where the correlations are going to have a model essentially by distance. So it's the cross correlations between locations. It's given the name Kriging in environmental and other disciplines. The general statistical procedure is called generalized least squares, and it can be solved by maximum likelihood instead of least squares. Maximum likelihood will allow us to include values that are less than the detection limit without putting in a number for them. So there's some other methods that I won't talk about today, but they're not as precise generally either. This routine that does maximum likelihood Kriging, if you want to think of it that way, is in another package. It's not in the NADA2 package. It's in a package called Sens Spatial, and that is already there at the CRAN site. So you could download that right now and load it into your R site and do Kriging. Here's an example of a graph of just a 2 variable lat long surface. And so the third variable is what is being predicted, some kind of contaminant or something. You can, in this, put in, actually you're kind of smoothing and taking them out, but you can put in other variables, think of them as X variables besides lat and long. So that's called a trend in Kriging, and you could take that trend out with those other variables, and then it's doing Kriging on what's left over, much like we did earlier with the GAM. It is a parametric procedure. It assumes, like Kriging does, other kinds of Kriging, it assumes that the distribution around the surface of points is a normal distribution. That's often not the case with us, so it's often that logarithms are taken of the y variable before things are Krieged, or in this case, censored Kriging is done. There's a term in here on the next slide called data augmentation, which I won't go into, which is just how when you've got data that are just only less than 1 and comparing it to a 3, how you figure out, it's basically that matching kind of procedure, but how do you figure out how far it is and how similar they are to each other? How do you estimate a variogram with that kind of thing? And since we took logs, this surface is a geometric mean. That's true whether or not there's censoring. In a paper by Fridley and Dixon in 2007, they looked at this procedure, this maximum likelihood for censored data kriging, and putting in a half the detection limit to see how well they worked. So I'm kind of ending where I started out. Don't stick in 1/2 the detection limit. There have been, for all of these procedures that I've talked about, there are papers in the statistics literature. Sometimes it's in our literature, often not, on evaluating things. Sometimes it's in the medical literature, but evaluating substitution. People have beaten that theme to death, and yet people still get papers published doing it. I don't know how. This I do know, because this is one of the earliest of the kriging ones that I've seen. But they compare putting in a substituted value to a better method, and they show that the substitution doesn't work well. So this is a smooth surface. That's the difference between two smooth surfaces, one with 1/2 the detection limit, one with the censored spatial, the surface that I showed on the previous slide. And the big differences are out here on the edges. I think there was a road going right down through the center here. Because they know what the data are, they know that the surface they did with the censored kriging was much more realistic than this one when they stuck in a 1/2 the detection limit. And it got worse as you got further away from the road. Maybe these are things that were contaminants in some way. And so if they had to be cleaned up, it would have said that the 1/2 result would have said there's much more contamination out on the edges than there really was, because of messing up the variogram by sticking in constants all over the place. And so there would be higher cleanup costs if you stick in a 1/2 the detection limit. So that's one of the consequences of doing that kind of thing. It'll come back to bite you. Ordonez in 2018 did the same kind of thing, just evaluating this data augmentation, how you build the variogram, and doing that with errors. The AIC errors, think of them that way, are lower with these censored kriging than they are with the DL/2 approach, of course. So all of this stuff has been studied, and substitution never wins. That is a quick survey of the many types of things that you can do. And I haven't even showed you everything. I didn't compare data to standards and a few other things. I didn't show you everything in the NADA2 package. But that package is implemented right now in our Nondetects and data analysis course at our training site, practicalstatsteachable.com. It's not free. The package itself will be available through the CRAN site January or soon after January. So that's the standard place to get our packages. The Spatial package and the ENV stats package that I mentioned earlier are available right now. And so they do some of these routines for censored data without substituting numbers. So you can do that already. Again, when the NADA2 package comes out, you'll be able to use the routines. It won't give you the information in this course on why they work and how they work. I'll just tell you, you could find some of that in a book that I wrote back in 2012 on statistics for censored environmental data. So it gives you some of the information, really probably for about 3/4 of the things I talked about today would be covered in there on how they work. There's some new stuff in the package that wasn't in that book. Also on the training site are other courses. These are 2 applied environmental statistics courses, and then a lot of free stuff. Sometimes when you go to our site, depending on whether it knows you or not, it might give you this, and then if you want to see the free stuff, you have to click the button at the bottom that says View All Courses. So there are a lot of free webinar recordings, just like this one will be, up on this site. This will be number 9, I believe, in the topic of Nondetects. There are already 8 there that are free and tell you some information. Not everything that is in the Nondetects and data analysis course. A little bit more than what I did today for each method. So you can find that at our training site. And today's video will be less than 9 there. And there's 8 others that deal with Nondetects that are freely available there that for your viewing. You can do that at any time. Today's recording will be there by the end of the week. And the PDF file will be found right with the recording, and the question and answers will be found at the recording. So they'll all be on the training site. This is the book. I've already mentioned it. I've already mentioned this, but if you have questions from today that you'd like to get an answer for, you can click the link on our Practical Stats Live page. So submit those, please. So do it now so that you can remember what your questions are. If you wait till tomorrow, you probably won't remember. I will answer each question, and I will put it along with the recording of this webinar. I do see a chat, so I will go ahead and answer it. So I'm going to have to sit down, and you won't see me, to read the chat window. In the chat window is, so I'm doing what I said I wouldn't do because I finished actually quite a bit sooner than I thought. From Asia, I hope I've pronounced it correctly. If not, forgive me. My last name gets mispronounced all of the time, so I understand. For AIC, you didn't substitute for sensor data, but you did have to indicate anywhere in your raw data that those values were below detection and give the detection limit. And the answer to that is yes, for any of these methods. That is what you have to do. So the information in Nondetects is what the detection limit is, and it's also the fact that it is below that detection limit. And there's a lot of information in that information. So that in general, you might say that with having a less than 1, it might be as much as 70 or 80% of the information that it would have been there if you knew that the values were 0.2 and 0.8. All right, so with that, I am going to end the video. Thank you for attending. And please submit questions and using that form, and I will answer them. We'll look for this on our training site, the recording, and the questions on the training site by the end of the week. Thanks very much, and goodbye.